So in today's video, we're going to talk about electronegativity and how electronegativity affects bonding. Okay. Now, if you recall, electronegativity is basically an atom's ability to attract another atom's electrons. Okay. Now, we could actually quantify this using what we call the Pauling electronegativity scale. All right, so this is the Pauling electronegativity scale, and then so we have quantified the electronegativities of elements. Okay, so here's just a small sample of the electronegativity Pauling's values of elements on the periodic table. Now we talked about this in the previous video, that electronegativity in general, it increases as you move to the right. Actually, let me use a pen, not a highlighter. It increases as it moves to the right, um, and then it also increases as you move up. All right, so we could see that there's an increased electronegativity in general. I mean, there's some variances here and there, but in general, that's typically the case. Where the most electronegative element is fluorine, and the least electronegative element is francium. All right, and so typically that's how you could kind of view this from a qualitative perspective. Okay, but quantitatively, these are the numbers, and these are the numbers that are given. Okay, now when it comes to trying to determine what type of bond that exists between two nuclei or two atoms, it all depends on the electronegativity differences between the two. Okay, and so to make this plain and simple, okay, um, if the difference of electronegativity, right, is between 0 to 0.4, between those values, all right, then we say that the type of bond that we get, all right, the type of bond that we get is what we call a non-polar covalent bond. All right, actually, it's me trying to preserve this. All right, non-polar covalent bond. I'll come back to the chart a little bit later. All right. Now, if the difference is between 0.5 to about 1.9, then we have what we call a polar covalent bond. Okay, and we'll talk about the difference between these two just a little bit later. Okay, and then if the difference between the electronegativities of the two atoms is 2.0 or greater, all right, then we say that the type of bond is ionic. And we know ionics, general, we always say between a metal and non-metal, but that's not always the case. But if you're really trying to determine what type of bond we have, then it really helps to have the Pauling values, and so that way you guys could calculate the electronegativities, because once you can calculate the electronegativities, then we know for sure, and we know for certain what type of bond we have, if it's covalent versus ionic, and then if it's covalent, is it polar covalent or non-polar covalent? All right, and so let's go through a couple examples so you can kind of see exactly what I'm talking about. All right, so like for example, if we're trying to compare, if we're trying to figure out the bonding between Na and Cl, all right, we will try to determine the values from both Na and Cl. So we're looking at the periodic table here. Here's Na. All right, so its Pauling scale is, or a Pauling value is 0.93. So 0.93. We go to chlorine, and we see chlorine's value is 3.16. So we'll go here to 3.16. All right. Now, electronegativity values are always positive. So I guess in this case, you just take the absolute value. All right. But it's always a positive number. So when you subtract the two, you get a value that is 2.23. Okay. Now looking at 2.23, now you want to be able to interpret that number. So if we go back to our table here, we see that values are just over 2.0, then we say that in this case, this is an ionic bond. All right, so between sodium and chlorine, we expect an ionic bond. Okay, so let's look at another example. So let's say we're trying to figure out the bond between a sulfur and an oxygen. All right, so here, okay, so we see that sulfur has a Pauling electronegativity value of 2.58. So I'm gonna write 2.58, and I'm gonna subtract it by oxygen, which I see oxygen has a value of 3.44. Okay, so I have 3.44. Remember, this is the absolute value because our values are always positive, and so we get, when we subtract those two, 0.86. So what does that mean? When we look at our table here, 0.86 fits under this right here. All right, so 0.5 to 1.9, so that we see that this is what we consider to be a polar covalent bond. All right, and so that's how we use this. Okay, now let's talk about the difference between covalent or non-polar covalent bond. Okay, spell non-polar covalent bond versus polar covalent bond. What's the difference between the two? Okay, well, one of the biggest differences obviously is the difference of electronegativities, right? The difference of electronegativities are different, right? So here we have, it's about 0 to 0.4. All right, then we could call that bond to be non-polar covalent. In this case, it's between 0.5 to about 1.9. That really kind of depends on what textbook you read it, but it's about there, right? 0.5 to 1.9. Then we could say that it's polar covalent. All right, so what's going on here? Well, remember, the main big thing about covalent compounds is that they're sharing electrons, right? There's electrons being shared between one nuclei versus the next. Well, in a non-polar compound, all right, the sharing of electrons, it's equal or close to equal. Why is that the case? Well, the electronegativity values are closer to 0. That means that the two nuclei are pulling the electrons with almost equal force. So it's almost as if you're playing tug of war with someone, and you're playing tug of war with someone who's roughly the same size, the same strength as you, well, that's going to be a long tug of war match, right? I mean, at that point, it's just going to be endurance. But I mean, there's not going to be you can easily see who could pull it much harder than the other because they're both equally as strong, equally as powerful, I guess, in the case. So that the sharing of electrons are equal. And so this is typically of, as I said, elements. So like, for example here, and if we could just quickly sketch and look. So elements that probably will show equal sharing, right? Obviously, elements is bonded with an element just like itself. So O2, right? That's obviously a nonpolar. If you think about O2 molecule, I mean, this bond is completely nonpolar because it's the same molecule, right? But then, but you could kind of, kind of look and see. Chances are, like nitrogen, oxygen, those two bonded together, that's about 0.4. Really, really close, right? So we could probably say that has very nonpolar properties, nonpolar covalent properties. Another example, we have like hydrogen bonding to carbon. That's another one, and that's about 0.3. So it has very nonpolar type of properties. Okay, so those are really, really good examples of nonpolar covalent bonds. Now, polar covalent bonds, all right, it's the electronegativity differences are a little bit greater. Okay, and so because it's a little bit greater, then one nucleus will actually tug on the electrons harder than the other, but not so much where it completely rips it away. And that's the thing with ionic. The electronegativity is so great compared to the other nucleus that it completely rips the electrons away. But in this case, it's not so much greater. All right, and so in this case, you have an unequal sharing of electrons. Okay, and so in this case, where you will have, so like for example, all right, so, oh, I think it isn't like SO. It's an example of this, where if you look, the oxygen has a stronger, has a higher electronegativity than the sulfur, and so because oxygen has a higher electronegativity of the sulfur, it has a greater pull on the sulfur. Okay, I mean greater pull on the electrons than the sulfur has on the electrons. And so how do we show this? All right, so if we're talking about the sulfur oxygen bond, and we know that the if we're talking about the case of electronegativity, right? We know the electronegativity is higher for the oxygen and it's lower for the sulfur, right? There is a, it's a covalent bond, so they're sharing, but one is much higher than the other. All right, then we say that the oxygen will be partially negative. Why do we say partially negative? Well, the electrons are going to be closer to the oxygens than it will be to the sulfur. So sulfur will be partially positive. So that sign, that sigma sign here, is just to show partial. Okay, so it will be partial, right? It's not a complete. It's not like in a sense of when we write NaCl, where Na is a positive charge, because positive charge is not partially positive, it is positive because it lost the electrons, where chlorine is negative, not partially negative, because chlorine lost the electrons. Okay, I mean chlorine gained the electron, right? But in the case of a polar covalent bond, it's a partial thing because they haven't completely lost or completely gained the electron. They're sharing it. They're just sharing it unequally. Okay. And so when you have something like this, we have what we call, in this case, we have what we call a dipole. All right. And our dipoles are just ends of molecules that have a partial charge. So here is a dipole moment or a dipole end of this molecule, because when we're thinking about the sulfur and oxygen, right, this side is partially negative, all right, while this side is partially positive. Okay, and this actually establishes some really interesting properties that we find in a lot of compounds, which we'll talk about in the next video. All right, so this is the biggest difference between polar and non-polar covalent compounds.